TS parameters. For all intents and purposes, this should have been one of my first presentations. I kept pushing it off until I felt like there was literally nothing that I didn't know about them. Several books into it, I'm still connecting the dots, so now's as good a time as any. Part 1, coming up. This is a loudspeaker, an electroacoustic transducer that converts electrical impulses into sound waves. There are many like it, each with its own set of characteristics, and in 1961 an Australian engineer by the name of Albert Neville Field developed the first set of alignment tables to predict the behavior of loudspeakers in sealed and vented enclosures. 11 years later, an American scientist by the name of Richard Small published a series of articles in the Journal of the Audio Engineering Society, expanding on Thiel's work and contributing to what we now know as the Thiel-Small or TS parameters, a series of measurements that define the electromechanical properties of a loudspeaker. That's the backstory. Now let's get into the parameters themselves, which we'll categorize as mechanical, electrical, and electromechanical. The mechanical parameters describe the physical properties of the cone and the suspension. The electrical parameters describe the relationship between the voice coil and the permanent magnet, and the electromechanical parameters, as you'd imagine, describe the relationship between the first two categories. Let's begin with the FS parameter. Just as a pendulum swings back and forth at a particular rate depending on its weight and fulcrum point, the moving mass of a driver in free air has a similar tendency to sway or to resonate, and the frequency of this action is measured in cycles per second, or hertz. This figure is often seen as the limit beneath which a driver will not perform, but that is not actually the case, and with suitable damping, a base shelf extension well below the FS can be achieved. Speaking of damping, the QMS parameter describes the driver's ability to control the motion of the cone, mechanically by way of suspension, and as the Q factor increases, the mechanical damping decreases. The VAS parameter tells us the volume of air that the piston would have to act on to create the same compliance as the mechanical suspension, so the smaller the value, the stiffer the suspension. And since it is presented as a unit of volume, it's often confused for a chamber size recommendation, which it is not. It's literally just an air spring analogy. And for its essential form, we look to the CMS parameter, which describes the suspension compliance by how far the cone will move when acted upon by a force of 1 Newton. The more it moves, the softer the suspension. Just as a side note, in physics, when we talk about compliance, we refer to stiffness, or the extent to which a physical object yields to an external force. Here's a brick wall. It has a very low compliance. I can't move it for shit. Here's a water balloon. Compared to the brick wall, it is very compliant. And now that I'm done with it... Next, there is the moving mass, described by the MMS parameter, which accounts for the weight of the cone, the voice coil, the former, half the surround, half the spider, and the air mass directly in front of and behind the cone. The RMS parameter gives us still another way to express the mechanical damping, namely as a function of the moving mass and the mechanical Q at the driver's resonant frequency, with the resistive losses expressed in mechanical ohms or mass over time. In fact, the next two parameters make for a straightforward example of how a given measurement can be expressed in a multitude of useful ways. Here I'm talking about the piston diameter and the area, both of which give us the effective rather than the physical value, so it's not just the cone but half the surround as well, since the inner edge of it does radiate some acoustic energy. And while we're on this, here's a tip. If you're measuring a sub and prefer not to eyeball the midpoint along the surround, just measure it from the inner to the outer crease, like this. And with that, let's move on to the electrical category, starting with the QES parameter. It gives us the driver's electrical damping, which opposes the mechanical one described by the QMS parameter. And again, the higher the Q factor, the lower the electrical damping. Next is the RE parameter, which describes the voice coil's DC resistance, or DCR. In the event of a dual voice coil driver, this figure is generally published in series to make the BL product look bigger, and we'll talk about that in a minute. The LE parameter gives us the coil's inductance, generally measured at 10 kHz, and the higher the value, the steeper the rate at which the electrical impedance climbs as we move up the frequency scale. You'll find this value to be especially low on drivers that are meant to play high, so mids, tweeters, and extended range drivers. With subs, there's obviously no emphasis on high-frequency performance, but as an inductor, the voice coil opposes any change in the current flow, so the higher the inductance, the slower the driver's reaction to changes in the signal, which ultimately hinders its transient performance. You want a fast sub? look for low inductance. Now let's talk about the BL parameter, which is a vector cross product of the permanent magnet's flux density, represented by the uppercase B, and the length of wire within that flux, represented by the lowercase l. Apply current, and the BL product gives us the raw motor strength in Tesla meters. However, since the flow of current is affected by resistance, comparing the motor strength of two different drivers by their BL product is only possible if they both have the exact same DCR value. Which brings us to BL squared over RE. Expressed in square newtons per watt, this parameter gives us the motor strength figure normalized for the ohm load. So if you're looking to compare drivers with two different coil values, this is the universal measure. And here's a practical example. Driver A is a 4 ohm woofer with a BL product of 10 Tesla meters. Driver B is an 8 ohm woofer with a BL product of 12 Tesla meters. At a glance, it might look like driver B has more motor force, but let's do the math. 10 Tesla meters squared is 100, divided by 4 ohms equals 25 square newtons per watt. 12 Tesla meters squared is 144, divided by 8 ohms equals 18 square newtons per watt. So as you can see, when we factor in the ohm loads, the driver with the higher BL product isn't necessarily the stronger of the two. Moving on to the electromechanical category, the QTS parameter combines the electrical and the mechanical damping, characterizing the driver's overall tendency to resonate at Fs. Think of it as a very general application guide. Values upwards of 0.4 indicate a tightly controlled suspension suitable for vented applications. Values between 0.4 and 0.7 indicate moderate damping suitable for sealed applications. And values in excess of 0.7 indicate minimal damping suitable for infinite baffles. The N0 parameter gives us the driver's reference efficiency in half space, either as a ratio of the electrical input to the acoustic output or as a percentage of the same. In fact, here's how we get the ratio, and here's how we get the percentage. Bear this in mind as we talk about the last item on our list. The SPL parameter indicates the driver's 1 watt, 1 meter sensitivity, which correlates directly with the reference efficiency. However, this is by far the most frequently tampered with figure, so if you suspect that yours looks a little optimistic, here's how you derive it from your reference efficiency. And there you have it. These are the small signal essentials used to simulate the behavior of any open back loudspeaker in any enclosure. I do have a few honorable mentions, and they are as follows. The Xmax parameter gives us the span of the linear cone travel presented as a one-way measurement from the resting position or peak to peak. The Xmech parameter gives us the cone travel to the physical limits of the mechanical suspension, again either one-way or peak to peak. There's also the VD parameter, which gives us the linear piston displacement volume as a product of the cone area in the Xmax. All three of these fall under the mechanical category, however they are also referred to as large signal parameters, used in high-energy dynamics simulations to map thermal compression, cone breakup modes, and other non-harmonic effects. In the electrical category, we have the PE measurement. This is another large signal parameter, and it gives us the driver's peak thermal power handling. Finally, in the electromechanical category, we have the EBP, or the efficiency bandwidth product, calculated by dividing the free air resonance by the electrical damping factors. There is an inverse correlation between efficiency and bandwidth, so the more you have of one, the less you get of the other. And in a fashion similar to the QTS parameter, the efficiency bandwidth product quantifies this trade-off to a single figure. Generally speaking, values below 50 suggest lower damping factors, which are suitable for use with sealed enclosures and infinite baffles. Values between 50 and 100 suggest compatibility with both sealed and vented enclosures. Finally, values in excess of 100 suggest high damping factors, which are best suited for use with just vented enclosures. And this is where we leave it off. In part 2 of this presentation, we'll talk about spotting parameter discrepancies, calculating missing parameters, and the overall importance of accurate data. So, like if you enjoyed part 1, subscribe for part 2, and I'll see you in the next one. Cheers!